Alright, so today we're going to be running through the 2020 external exam for engineering, the multiple choice and the question and response book as well, just because the marking guide, especially for engineering, although just across QCAA, is just horrible. There's really no other way to put it. It's just really bad. But yeah, let's start. So this is a really simple one. This is just saying that you got to know that this is a... Ooh. Where'd my pen go? The hell? So this is just saying, alright, this is a worm gear. And so this tooth here, the ridges, are going to run all around the outside of this, and it's all one tooth. So, and you're also going to need to remember formula gear ratio, although actually you're not going to need that at all, because none of these are reverses of each other, so it's just asking you to count the teeth. So if we just go to a quick count, we're going to see that this worm gear here has 18 teeth, and this one has 1 tooth. So the answer is going to be C. And then this is just your basic incline slope now. From the IA3, this formula is pretty well burnt into my head. Let me write it down. So this formula here, it's not the one I'm going to be using here, because if we're going down a slope, we are going to, the force here is going to be equal to this, but if we're finding the force required to go up a slope, it's not going to be, we're not going to have that minus, instead we're actually going to have a plus here, because it's inclusive of that frictional part that we need to overcome. And just looking at the question here, we are getting pulled up the incline, and we're looking for the minimum value when mu is 0.4, and that's static mu. So what we're going to do there is let's bring this over here and simplify it a little bit. So we can have mg on the outside sine theta minus mu cos theta. And my tablet broke again. There we go. And it's going to be 25 times 9.8 sine of 25 degrees minus 0.4 cos 25 degrees. Make sure your calculator is in degrees, and you won't be able to bring your scientific calculator into the exam either, so don't get too used to that, and especially don't get used to being able to access and solve, because you can do that for some of these questions, especially moments questions. It's really handy, but there isn't actually many of those on the exam anyway, you'll find. So if I just go put in sine 25 plus cos 25 times 0.4, I'm going to get 25 times 9.8 times 0.7851. When you're dealing with trig and you want to write down the numbers and then go to another stage, I would highly recommend just writing 4 digits, because again, rounding can really catch you off guard with these questions sometimes. It's going to give you 192 newtons, which we can see over here. The answer is A. And for question 3, you're going to need to know your microstructures. This is a pretty easy microstructure question we've given you here. And if you can see, you've got these lamellar lines coming out there. And that's lines of the dark is ferrite, and the light is cementite. And those are lamellar, a lamellar arrangement of these different phases. And so that section is likely going to be ferrite, and this entire area is pearlite. So the answer is B. Austenite, we're not going to see austenite in here, because by the looks of it, this is a fully cooled microstructure, meaning it's below the eutectoid point, and we're not going to see any austenite ever below the eutectoid point. Now this one's actually a little bit easier than you'd first think, but I would highly recommend for cables and materials, use memorization strategies. Like, there is a website called Blookit, which is like you play a game and it asks you lots of questions. Really fun and competitive to play with friends. I've made a few quizzes on there, especially about plastics, because it was hard to remember initially, but I started playing that, played it a few times. I don't think I'm ever going to forget my plastics ever again. If you just type in the search bar like QCAA engineering plastics, and you see one with like 72 questions, that's mine. And you're going to learn that you only need to know 6 different plastics in the syllabus, and that's going to be PVC, PE is polyvinyl chloride, polyethylene, polypropylene, acrylonitrile butadiene styrene, polylactic acid. What's the last one? Nylon, of course. Nylon is probably the easiest one to know. But instantly, seeing all this, you can instantly rule out it's not polystyrene because we don't talk about that. And it's not, you're going to have to know your plastics for this one, but it's not polypropylene either. And that's because the only ones that are used for cable insulation is PVC and polyethylene. And PVC is generally used for low voltage, while polyethylene is high voltage. This is just a memory thing that you're going to have to learn. But it is really helpful, this booklet here, and it helped me on my last exam just this year, a couple of weeks ago. And the answer is C, polyethylene. This is the question that I probably don't like the most on this exam, because it is really deceptive. You've got an input here and an output here, but the question, if you read it, a screw conveyor is used to transport grain from an input chute up to a 10-degree slope to a holding bin using the specifications shown, which is this table here. What is the volume of grain moved each minute? Now this is really, really tricky if you have a look at the marking scheme. This question here, when you read it through the first time, doesn't actually mean what you first thought it did. It's not, the question isn't asking how much grain in the time frame is coming through the output, as you would think from this diagram here. It's actually how much grain is being physically moved. And so if we do that, we're going to need to have a closer look at these specifications. So we've got, we're working in minutes, and we've got RPM here, so we don't need to do any conversions there. If we know the screw length, so the screw is this entire Archimedes screw that goes from about here to here, and okay, alright then, that's going to be 2.4 meters. So if we go 2.4 meters and divide that by the screw pitch, which screw pitch is the length between those ridges there, that's going to tell us how many different little pockets we have for moving the grain. So if we do 2.4 divided by 0.15, we should find that there is 16 exactly 16 different pockets. And if we times that by the capacity moved by each, I don't like that wording there, it should be pocket, not screw, because the screw refers to this thing. I don't know why it's called screw, but we're going to times that by the capacity, and then times that by the conveyor RPM. And you're going to end up with 24 meters cubed of grain moved per minute. If you did it the other way, you're going to end up, which makes sense given the grain output, and you do how much grain is comes out, it's just going to be 10 times 0.15, which is D. It's not that. They're really tricky with the wording here. It's really annoying, and I really dislike them for it. But the answer for this question is B. This is just your standard work and potential energy here. So let's have a look at this. For this, we're going to need power is W on T, and work is force times distance. So I lied, it wasn't potential energy. If it doesn't say, assume the system was out without friction and that 1 liter of water has a mass of 1 kilogram, you should always assume that. Sometimes they won't say it. And we're working in hours. So, if we do work equal, far out, force times distance, the force is going to be 10,000 kilograms times 9.8. And then we're going to times that by the distance of 100 meters, which will give us big number, 9.8 megajoules. And mega is just a million. And so if we assume that this system is 100% efficient, then our power is going to be work divided by time, which is just going to be no, we do have to do some conversions because it's in per hour, and we are always, for power is, well, the watts unit requires seconds, so we are going to have to convert this to 9.8 million. We're going to divide that by 60 times 60, which is 60 seconds for 60 minutes, which is our hour, and that's going to leave us with 2,722 watts, and if we compare that to 7,450 by dividing it, so we're going to take that and divide it by 7,450 watts, it's going to leave us with a percentage of 36.5%, and that's going to be B. Alright, let me move some of this stuff out of the way. Question 7. Let's draw a picture for this one since there isn't one already. 20 kilogram box. We're looking for the angle here. So, the coefficient of static friction is 0.27. It's the angle of repose. Now, I don't believe we're supposed to know that. I don't think that's actually in the syllabus there. It's supposed to be quote, end quote, common knowledge, though I've never heard that word before doing this. But that is just this angle. So, I don't know why they decided to use funny wording, but, you know, QCAA. And so if the box is sitting on the point of sliding, it's at rest, then from knowing our formula for final force on an inclined plane is mg sine theta minus mg cos theta, mu mg cos theta, we know that that force is 0 because it's not moving, so we can move mu mg cos theta onto the left side and set that equal to mg sine theta. And if we do a little bit of rearranging, you'll notice that we can cancel these two and move the cos over to this side, and we get mu is tan theta. So rearrange for theta, and we get theta is tan inverse of 0.27. Chuck that in the calculator, and you'll get 15.1 degrees. And that is going to be answer C. We won't use any more space for this question. There's not going to be too many logic gate questions. I don't think there will be another one in this format on the question response. Not question response. There will definitely be a question response question, but it will be making a logic gate, because they ask you a question for that every year. But there probably won't be this question on multiple choice, I think. Don't take my word for granted there, because QCAA can be surprising in many different ways. So, for knowing your logic gates, you should identify that that line there means it is an X special, and that curve on that arrow there means it's an OR gate. So, this is really just a general knowledge question. You know, if you've got 0, 0, 0, 1, 1, 0, 1, 1 for your two entries, P and Q, then your F, we've got none, so 0. We have one or the other. We have one or the other. Now, because it's XOR, it's one or the other, but not both. And here we have both, so it's 0. And now we should just be looking for that pattern there. So it's not that one, it's not that one, not that one, and there it is. So it's A. Alright, so we've got a velocity ratio of 1 to 3 here, and we also know the diameter of the rear tire, and we're looking for the distance travelled. So we know our velocity ratio is going to be distance of effort to distance of load, and if we transfer that, we're going to know that it's going to be pedals, because that's where we're putting the effort in, to rear tire. And if we're doing 3 rotations of the pedals, that means we're going to times this 1 by 3, and therefore times the other side by 3, and we're going to get 9. So we're going to have 9 rotations of the rear tire. To know how much distance, first we're going to find out the distance that one revolution of the rear tire is going to take, and we know our circumference is just 2 pi r, so jump over and go pi diameter, and times that by 9. And then that is all going to come to 9 times pi times 0.74, don't forget 0.74, not 740, not 7.4. Chuck that into your calculator. And we're going to get roughly 21 meters. And that's answer B. This is just a general knowledge question, again. So, you should know a lot of things on your graph by this point. If you don't, you should really start considering to do that. So, this area is called strain hardening. And then the following area after the ultimate tensile strength point is going to be necking, because you're like, the material's pulling on itself, it's getting thinner just before it fractures. That's why it's called necking and fracturing. You get that? Fracture point. And this is going to be our yield stress. And so, obviously, not that one. It's this one here. Why? It's not the plastic limit because it's the beginning of the plastic region. This is the elastic region. And this is the plastic region. Young's modulus. So that is pretty much any point along here. It's really just the gradient that they're worried about. It's not particularly a single point. The most similar thing to this would be the proportional limit, which you'd say is about here. That's when you can't use Young's modulus anymore to figure out the stiffness of the material. Because Young's modulus is also just stiffness. And they might ask you a question on that. Because they did in my last exam, I'm pretty sure. The other thing you're going to need to know is that strain has the other name of elongation, which is going to be a percentage. And the area under the curve is the toughness. And how much elongation it can resist before fracturing. So at this point here, that's called the ductility. And they have asked questions on pretty much all of this before. So you will need to know this. And that's the multiple choice done. So here comes the hard part. Let's bring this up to the top. So this should... Whoa. My pen's gone crazy again. Ideally, this shouldn't take you... Look, the way I do this in my exams is I use this perusal time to first look through all the questions and have a little idea, mostly in section 3, where the harder questions are, what I'm going to need to do roughly, take some guesses, look at the marks, what I'm going to need to do, and that might take like half of the perusal time, and I'm going to spend the other 5 minutes doing multiple choice, and I'm actually going to be doing the multiple choice, not by picking up my pen, but just using my fingernail to make dents in the paper for my answers, just on top of like the A, B, C, D. And it's really helpful because with this you can do some of the math in your head and, you know, whack out like 5 or 6 questions maybe. And that is really helpful because that's 5, like, you just get another like 4 minutes to work on a question if you're struggling. And yeah. Let's start here with the question section 2. It's going to be relatively easy. It's the proportional limit of a material as indicated on a stress-strain diagram. Provide an annotated sketch to support your explanation. Alright, so first of all, let's just draw a stress versus strain diagram. And we're going to mark this point here just before it starts, the gradient starts changing, and we're going to label that proportional limit. And I'm also going to include my axes because if they might mark me down, I'll check that in a second. Strain there, stress up. That is a horrible straight line. So yeah, they could take a mark off you if you don't put that axis in there, because it does say provides an appropriately annotated stress-strain diagram sketch. So you're going to need to have that, and you're going to need to have the axis as well. And for the explanation, we'll say proportional limit. Start with the subject. The proportional limit is the last point at which Young's modulus can be calculated. I cannot. What else does that talk about, really? Represents stiffness. Now this is, we got 1 mark for, I'm missing a mark here. Not quite sure what it is yet. Because we've got 1 mark for the diagram, and we're going to probably have 1 mark for Young's modulus. And represents stiffness. See, this is the thing with the QCAA questions that I really don't like sometimes. I promise I'm not being salty. This is... But the answer that they give is the proportional limit is the greatest stress that a material can withstand. without losing straight line proportionality. Like, I guess that's pretty much what I was saying, but in more ridiculous words. Between stress and strain within the material's elastic limit. Oops. Oh my god, that is horrible writing. Strain within the material's elastic limit. I'm not sure that realistically you should be expected to have this last part within the material's elastic limit, because it's not really what it's asking. What it's asking is the first half of the answer that they've given. And they do this with a lot of questions, so you should make sure to just try to include everything you know if they ask you. An explanation, if you do physics as well, which is highly likely given you're doing engineering, you're going to need to do that as well. It is a really easy exam, but when it comes to explanations, if you don't know just to word vomit everything you know, all the formulas, you're going to lose marks really easily. But really, you shouldn't be expected, I don't think, to include this. So who knows? Maybe they don't mark it. They mark it generously. This is another knowledge question for plastics. Again, if you go to the Blooket website, it's really helpful for this. I know all my plastics really, really well. It's really amazing. So what you're going to first know about polylactic acid is it is biosafe. It has, meaning it doesn't have any, like, it's not going to harm you, it's not going to leak, it stays where it is, it doesn't poison you or anything. It's really quite self-explanatory. The other thing is it's going to have good layer adhesion, which means it's really good at staying all together. It doesn't delaminate when you form it into screws and, you know, screw it into bone to put a plate in or something. That's also going to help it really, really well. So another thing. The other thing I can remember off the top of my head is that it has a low melting point. That isn't particularly helpful here. Just trying to dump things that I remember for this plastic. Oof. Oh yeah, okay. It has a really... Whoop. It has a really high tensile strength, which makes it, you know, again, really good for these applications. The tensile strength is really good because it's going to let the screws go into the bone and, you know, with a good amount of force, be able to hold something there. But I can't really think of a fourth answer for this, and, you know, again, what they've done is their answers were... I'm not this could get 4 marks, this answer here, but it is kind of incomplete. But that's debatable, because their answer is biodegradable, high tensile strength, non-toxic, and resistant to chemicals. Ideally, I should have remembered that last point. But also, you could argue that, obviously we've got this one here, and this one's new, but biosafe could be linked with biodegradable and non-toxic, because really it could be, it's closer to non-toxic though, so either I would have included biodegradable or resistant to chemicals, although that's not necessarily, we're not supposed to know that, really, for polylactic acid. But yeah, I should have put resistant to chemicals in there. 4-mark question, let's move on. Now, they didn't have this in my last exam, which is really great, because these questions, they suck. And they're not hard. It's just, it's ambiguous, sort of. Alright. 62% tin, 38% lead, binary alloy. So this question is, I feel like it draws too much, because it is a niche thing that it's asking for. You're supposed to know that, first of all, tin and lead are not isomorphous, but also, this specific combination of 62% tin and 38% lead, actually, on the phase diagram, that's actually the eutectoid point. So that's going to be the point where both phases uniformly solidify all at the same time. And because that piece of information is so important here, because we need to know that that means that we're going to form a really lamellar structure similar to perlite, but with lead and tin, because they're all solidifying at the same time, and we're not going to have, you know, flat phases where some tin, some lead is dissolved in a tin, because that's only going to happen in these regions here. But we're not at that point. We're at the eutectoid. And so what the question's asking us is we're going to draw some cell lines here, some grain boundaries more specifically, make it a little natural. Don't spend too much time on it because, you know, time's precious. And you probably want to make these lines a little thicker, just to really make sure it's visible to those exam markers. Just make those... Now that we've got those grain... Really? Now that we've got those grain boundaries done, let's just draw in some lamellar lines, making sure these are all going in roughly the same direction for each grain, but separate to the grain. They need to be going in different directions, because that's the reason that grains form. Grains form because when they're solidifying, and you've got all these little dendrites that are forming, they're all going to have lines. And when you have multiple dendrites, you know, they're going to... as it cools, they're going to expand, and these lines aren't going to match up. So as these expand, you're going to get a line here, because it's going to go out there. You might get another dendrite in here, which gives you your funny angles, but they're not going to be in the same direction. They might be a little bit off. They might be... See, that's going to be wrong there, because that's aligned. So let's draw it like this. You can't have them in the same direction. They might drop you marks there. It really depends on the marking criteria there. But we get a point there for the lamellar structure that we've drawn, and we also get the... Ugh. My bad. I did not do any annotations. So let's do grain boundary. And this is going to be 62% tin, 38% lead, and that's going to be another point for that. Don't forget your annotations. Now let's move this out of the way so we can do a explanation. Alright, so the other thing you're going to need to know for this explanation is that that is the eutectic temperature, that line there. What's also known as a solidus line, it's also the eutectic temperature, the lowest melting point of a mixture. And that answer for the explanation is that microstructure changes occur when the cooling of the completely soluble liquid solution reaches the eutectic temperature of 183 degrees Celsius. You shouldn't need to know that. Especially for tin alloy, it's not in the marking criteria. You won't need to write the exact temperature, especially for lead and tin binary alloy phase diagrams. Now here the liquid solution completely freezes to become a totally solid eutectic mixture with partial solid solubility. You don't need to mention partial solid solubility because this is not... We're not looking at solubility regions in this diagram as the temperature continues to fall. And what they're saying there is just, it's a... They didn't even explain... You gotta be careful with these questions, because that actually, if you have a look at the response marks, that actually only gets 2 out of 3 marks, because they mention in the marking criteria that you get a point there for mentioning it's a laminar structure, but they haven't done that. So... bloody funny. The other 2 marks is just mentioning it's a eutectic mixture, and that the mixture solidifies directly from liquid to solid, so just saying it's a eutectoid composition. It's going to happen at the eutectoid point. And that's going to net you 4 marks. This is the logic gate question I was talking about. It's always going to pop up in the question response. And it's either going to be in this format where you make a truth table or you make the logic circuits. Making the truth tables really easy. You shouldn't have a problem with this. It's the only logic gate questions. If you see a logic gate question where you have to make a complicated circuit, you're going to spend a great deal of time there. Be aware of that. And my pen's broken again. Alright. Okay, so we have a NOT gate here, that's an AND gate next to it, an XOR gate, and a NAND gate. Okay, so that is all the possible combinations. I've got there full zeros, ones, twos, and the 3. So, given that we've got a knot here, this AND gate, let's make this a little bit easier on ourselves and actually take that off. And let's label this D and this E, and let's put those in there as well. So D is only going to be on when A is off and B is on. And that's going to happen here. And here. So it's only going to be on 2 different times, in 2 different situations. And for E, as long as B and C aren't on, both on, it's going to be on. So on, off, off. And then S is an XOR gate, so it's one or the other, but not both. So that's on, off, because it's both on. That is your answer. Ah, my bad. Far out. So because it's both off here, both off, so that's a 0. Far out. Now the marking guide, again, I don't agree with it, because it does say to include another, like, additional area for this gate here, but I don't think that's necessary. You should get full marks just for doing this. Now, this is an explanation question. I hate these with a passion. They are, I don't think there's any really, like, useful, I don't think this is useful in any sense. Explain why an engineer would recommend solar power water pumps for crop irrigation to a community in a developing company. For 3 different types of technology knowledge, identify 2 factors of each to support your explanation. So you're just going to mention 3 different types of technologies. So you could say, or fields, so you could say, what, mechatronic for the water pumps, mechanical for water pumps, mechatronic is not, this is not mechatronics. Solar powered. You also have software for the water pumps. So, water pump control. The pump itself. And environment, they want you to identify... Oh, I hate this. See, it says technology knowledge. It says technology knowledge. And then, looking at the answer, what they actually want you to write is 2 factors of... can't spell. 2 factors of environmental... 2 factors of economics, and 2 factors of sustainability. So try to remember these 3 if you can. I'm probably going to do that again. So they just want you to mention 2 different factors of each, and it's really, I don't think this is intuitive at all. And they're going to want you to say, like, is the area sunny? What's another thing they want you to say? Do crops get enough water? Economics. Can this be afforded? Is solar water panels, water pumps are cheap in the long term? Sustainability. How is... what can we think? Maintenance. How is maintenance going to work? I can't think of a last one for that, or I'm not giving this much time either. What do they say? They say... basically ask, again, is the area sunny? They also have a really long explanation, though I don't think you need necessarily an explanation for these questions. It's all about factors, the marking criteria. Just mentioning them. They talk about initial cost being high, but running costs are low. So essentially what I've asked, I have put those points in. They also ask it would be important to have a sustainable water supply. I don't see how that is really... Never mind, yep. For some reason you're supposed to know that solar pumps are able to supply large volumes of water. It's a very niche thing again. And... yeah, okay, they didn't really include those relevant factors again. They really just listed off things. Didn't even list off factors, they just explained one thing for each different category, seemingly. Let's move on. I hate those questions. So this is 15 teeth. Gear B has 30 teeth. Use a platform, a distance is moving 1.2 meters. The teeth of Gear C have a pitch of 10 millimeters, and Gear B has 30 teeth. Identify the gear train used. The hell? This is not a gear... I would not call this a gear train. What we're looking for is A to C. And what we're... this is a rack and pinion here. So that's a pinion gear. That's a rack. It's going to move the platform up. Very simple. So... C is, for some reason, there's a mark dedicated to stating that C is a rack and pinion. Is a rack. And B is a pinion. And I hate that because it's not what the question is asking. I don't know. I don't know why. I don't know why they do this. It doesn't make any sense. Yeah, they ask you first for... that's the first mark. And then the rest of it... what? Okay. So to move at a distance of 1.2 meters, and each tooth is 10 millimeters apart, that means that we are going to have, just doing some quick math, that's going to be a C has 120 teeth, and that means that the gear ratio from B to C, we're going to have, because this is 30 teeth, it's going to require 4 revolutions of B to move the platform. Okay, I give up. Can't write properly. And so if A to B, if it takes 2 revolutions of A to move B, then it's going to take 8 revolutions of A to move C. And I don't understand. So they have this sentence at the end of their explanation. They say, therefore, the gear ratio of gear A to gear C is 1 to 150 millimeters. When it's clearly... where do you get the millimeters of A from? We're not given that. We're not given that. If it takes 8 revolutions of A to move C, the max we could do next is do 15 to 150 teeth. 100... it's getting messed up. 120 teeth. Which... is going to again just reduce down to 1 to 8. Which is the opposite, so that's not... that's not the gear ratio. A to C is 8 to 1. I don't know what they're on about, but they're saying something about millimeters. It's wrong. We have to do this. This is what the question's asking for. Now this question... this is definitely one of the easier explanation questions. So, you're going to need to know your carbon compositions. And again, this is a mental memory thing, and I've made booklets for this. It's really good, really helpful. It's completely free. Highly recommend it. First thing you need to know is your high carbon steel carbon percentage. So HC steel is 0.6% to 1.25% carbon. And next we're going to have to link that to two of its mechanical... Why did that give me an error? Next we're going to have to link that to two of its mechanical properties in the context of two industrial applications. Alright, so the marking distribution is pretty simple here. We've got one mark for this statement here, we've got one mark for each of mechanical properties, and one mark for each of two industrial applications. So, high carbon steel, because it's got so much carbon, most of it's past the 0.8% carbon, which is going to make it a eutectoid mixture of carbon and steel. And because it's eutectoid, we're going to start seeing the formation of pearlite, but we're still going to have a decent amount of ferrite. Let's say it's about equal ratio, maybe. Probably not. It's probably less pearlite than ferrite. And the pearlite is going to give us a really strong, stiff properties, but the mixture of ferrite is also going to make it ductile. So when you mix these two together, you're going to end up with a strong but not brittle material. It's going to be on the lower range of strong materials. Still going to be a little bit malleable. You're going to be able to somewhat be able to use it. It's going to be durable and hard, but it's not going to fracture that easily. Like ultra high steel, if it's not tempered, is going to fracture a lot, which is why it's usually highly tempered, and that's why it's usually non-industrial, because when it's industrial, we want it to last long. And so we could just we should know this. This is well, you shouldn't really be. It's a lot to remember, but you should know this. Two industrial applications. It's going to be industrial knives, high-strength spring materials, wires, and punches, tools, etc. And that's also non-industrial. Sorry, industrial. So there we go. We've listed mechanical properties: strong, stiff, and ductile. You're going to want to go in a bit more detail there. Just done a little overview. And two of these. Moving on, section 3. Now you're going to want to spend maybe 40 minutes of the exam in here if you want to get most of it done. Alright, we've got a slope of 30 degrees. So acceleration was g on 3. Alright, so we did a similar working before. We're going to know that mu is going to be tan theta, because the mass and gravity, they cancel out in the final force equation. Okay, so that's going to be tan of 30 degrees, and that is 0.5774. But that they want us to round to 2 decimal places. If you don't do this, don't freak out, because in a lot of external exams, they completely disregard this in the marking criteria and will accept any answer as long as it has 2 or more decimal places. And resulting static friction. What? Yes, okay. So resulting force of static friction, obviously that's different from static friction, and this is in your formula sheet. So friction force is going to be mu SFN, where that's the normal force right there. You got to remember that friction force is, you got to remember normal force isn't just mg, because when you have an object on a plane here, sure, that's going to be mg, but that's not the normal force. This force here is actually mg cos theta, and that's Fn. So it's going to be mu s mg cos theta. And substitute, always make sure to substitute, even though this is a 2-mark question. Sometimes they're ridiculous where they put the marks. times 900 times 9.8 on 3 cos 30 degrees. Cos 30 is a half, so 0.58 times 900 times 9.8 divided by 6 times cos of 30. So 1,478 newtons is the correct answer. That's my bad. I divided by 2 twice. Don't make that mistake. Now the last part of this question, 2 marks. Explain what would happen to the coefficient of static friction if the machine was tested on Earth. So you get 2 marks here. One's probably for mathematical reasoning, one's for the correct answer. So wait. So mu s is tan theta. It has no dependence on gravity. It would not change. Okay, so the marking there, they say 1 mark for saying mu s depends only on the angle of repose. Again, that word. But I don't think you'd have to say that. As long as you say this formula and it has no dependence on gravity, you shouldn't need to mention that it has an angle, only depends on angle of repose, because that's just not what the question's asking. Alright, so this is rearrangement. So let's go and put in a P equals W on T. Rearrange. W equals PT, which equals 4355 times 90. And that's 391,950 joules. And we know that work equals force times distance, and we're going to sub in right here and just do mgd, rearrange for m, w on gd. It's going to give us 391,950 over 9.8 times 20. It's going to give us 2,000 kilograms. Oops. There you go. Second half of this question. Determine the velocity on impact of a 5 kilogram scrap metal that falls to the ground unobstructed from the bin. So this is suvat, obviously. We don't have u, and we have negative acceleration. So s equals negative a half 9.8 t squared. We will need to rearrange for t to sub in. So that's going to be negative 2s, root negative 2s on 9.8, which equals root negative 2 times 20 over 9.8. And that's going to give us, let's just make that positive so we can have easy calculation. 40 over 9.8 root. So that's 2.02 seconds. And if we've got velocity, velocity is just going to be v equals u plus at. Again, we don't have an initial velocity. So acceleration times time, which is going to be 2.02 times 9.8, which should give you about 18.920. Yeah, it's going to give you 20. Ugh. 20 meters per second. Okay, this one, again, you probably haven't been taught this specifically. I don't think we need to know this. I don't think this is in the syllabus. Double-threaded worms. But it is somewhat intuitive, but, you know, it could be a 50% guess. So double-threaded worm is going to have half the pitch, and it's going to essentially just have 2 teeth, and that's all you need to know. So this has 2 teeth, and this has 40 teeth. Efficiency, we've got here 45%. Alright, so this is just a velocity ratio, mechanical advantage, rearranging. Very simple, very common. Let's just write out the formula. So MA equals efficiency times VR, where VR is going to be Distance of effort divided by distance of load. Oh. Okay, so it says here that the effort is on the worm wheel, so it's going to be 0.45 times 2 over 40, which gives us a very small number of 0.0225. Huh? Oh! That is my bad. I mixed up a worm wheel and threaded worm. So that is... Sorry. So it's going to be 0.45 times the worm wheel, which is the 40-tooth worm wheel, over the double-threaded worm. So 0.45 times 20... What's that? I should have been able to figure that out. It's 9. And so mechanical advantage of 9, if we're using an effort of 50 newtons, it's just 9 times 50, and it's going to be 450 newtons. And an effort wheel is added to the worm axle, decreasing the efficiency of the compound machine to 36%, determine the velocity ratio of the added component, answer to 2 decimal places. So, this is an interesting question, because this is another thing that I don't think... Is this on the formula sheet? It's not on the formula sheet, and I have not seen this in the syllabus before. So this is testing your understanding of something really niche again. I swear, it's always something niche. So it's efficiency total is efficiency 1 times efficiency 2. So we can just plug in some numbers there and rearrange. You know that 0.36 is going to be 0.45 times the sum efficiency of the effort wheel. And so if we divide 0.36 by 0.5, we're going to find that efficiency 2 is 80% efficient. And if we identify that the mechanical advantage isn't going to change for this, the velocity ratio is what is changing, then we can rearrange for velocity ratio, where VR equals MA on efficiency 2, which is 9 over 0.8. That's 1.2 times 9, which is 10, no? 11.25. My bad. And that's all the working for that question. Is this not? Never mind. Alright, so we've just got a 50-50% alloy at 1400 degrees Celsius. So let's draw a line there and a line there. Oops. So let's say that we've got 45% at the alpha, C alpha point. That's that point. That's the CO point there. And over here we're going to have our CL point at 80% A. And that's because this is the point where we have alpha, this is the point where we have liquid, and that's the origin. So we're looking for percentage portion of solid and liquid, and that's pretty easy. It's going to be W liquid. It's going to be C alpha minus CO over C alpha minus CL. You can either remember that, or you can remember that if you want the right side, then you're going to take the left portion, the left side of the origin point, divided by the entire length, because that's what we're doing in this question, in this section here. So, you gotta be kidding me. So, let's just sub in 45 minus 50 over 45 minus 80. And that should give us... Why? 5 over 35. Or 1 over 7. Therefore, WS is going to equal 6 over 7. Oh, okay. Ooh. 14.29% over here. And 85.7. 1 here. Very simple question. And, oh, wait. They said answer to the nearest whole unit. Very sorry. Right there, so 86% and 14%. And right there you get... I can't really see where the marks are going in this question, so I'm just going to take a little look at the marking scheme, and you get a mark for the diagram annotations. Then we get correct use of inverse lever rule. Then we get correct working, so this here. And then it says provide correct use of the inverse lever rule to calculate liquid again, but that shouldn't be there. It should just be work one out from the other, because you don't need to do the inverse lever rule again. You can just do one minus the other, because they all have to add, it has to add up to 100%. So that'll be the third tick, because yeah. And so we've got 1, 2, 3, 4, and then it's another mark for this one here. That's 5 out of 5. Alright, because it says constant velocity here, it means that acceleration is equal 0, which means we can't use suvat. And so what we have to do now is, because acceleration is 0, and that means that the force of mg sine theta and mu mg cos theta are equal to each other. So we can say cos theta equals mu cos theta equals sine theta, and mu is tan of 20 degrees, which gives us 0.36. But if we modify this so it does accelerate, or decelerates, we want to decelerate, then we are not going to have mg sine theta equal to mu mg cos theta. Instead, we're going to start off with, let's start off with v equals u plus at. So we know that final velocity is 0, initial velocity is 1 meters per second, plus an unknown acceleration times an unknown time. So let's rearrange for time, and we'll see that we get minus 1 on a. I'm going to take this over to the right and do suvat. Let's swap these around. S equals ut plus half at squared. So we can rearrange that for a, and we're going to get... That's a pain. Let's not rearrange that for a. Instead, we're going to take it down here, and let's sub in our formula for a. Okay, that's subbed. Initial velocity, 1 minus a half, it's going to give us half, so t equals 6. Follows that, acceleration is going to be negative 1 over 6 then. So now that we know that what our acceleration is, we can say, we can bring in our formula, mg sine theta minus mu mg cos theta, and let's set that equal to ma, and now we can immediately cancel all these m's. We can't cancel the g's. And if we want to rearrange for mu, so that's going to end up looking like a on g minus sine theta minus over cos theta. And it's a sub in. negative. It's already negative. Wait. Let's get the plus in. Cos of 20 degrees. And that is going to equal 0.38. And now it's asking for the difference, which is just 0.38 minus 0.36, which equals 0.02, and that's the final answer. And the marks there, let's have a look. Correct force of friction. We don't need to work that out to do this question. There's... yeah, okay, so the marking criteria for this one's also scuffed, because it wants you to give force of friction and correct normal force. We don't have to do that, because we can just rearrange and skip, because we know. They should not... This should be general knowledge. You should not need to provide the correct working for the force of friction, but I would do it anyways, if I wasn't stupid. But they're likely going to give you the marks anyway. Just the marking scheme on these past papers is horrible. It also wants you to give correct coefficient of kinetic friction and correct formula, so that's alright. And then it's deceleration, correct working for deceleration, force of friction for deceleration. Again, that's really not necessary, because you can skip it entirely just by knowing setting formulas equal to each other. You don't have to calculate it. I don't know why they're giving you marks for it. Provides correct working, gives correct answer. Alright, so now we have the last question. Question 23. This one is honestly really easy. Rate design velocity. So we have a elevator. Wants us to draw a picture. It's going to accelerate until it reaches v of 10 meters per second when u equals 0. It's 2,500 kilograms. So let's draw this mg, which is going to work out to be 2,024.5 kilonewtons. And then ft, where ft is going to be 30 kilonewtons. So we can just subtract the difference between these two forces to find a resultant acceleration if we divide by the mass. So the difference here is 5.5 kilonewtons. Divide that by the mass of the elevator. It's going to give us an acceleration of 2.2 meters per second squared. Now we need to find how long it takes it to get to 10 meters per second. So it's just velocity equals u plus at. U is 0, so it's 2.2. 10 divided by 2.2 equals t. And that's going to equal 4.55 seconds. And the distance it travels, now that's just suvat. So s equals ut, but u is 0, so half at squared. Half 2.2 times 4.55 squared. 1.1 times... oops. 22.77 meters. And I think it said round. Yeah, so 23 meters. And we're done.